Uh, okay, so I'm going to take solace in what Natasha said a moment ago. Everything will be fine. And so, um, yeah, I've my talk is about rhombohedral graphene. There will be several talks today about rhombohedral graphene. I've taken my title, Hitchhiker's Guide to Rhombohedral Graphene, from the 1980s British science fiction satire, which tells the story of Ford Prefect, the uh, um, um, uh, researching our galaxy for his alien civilization. And it's fitting for the analogy between galaxies uh, and graphene is fitting because in rhombohedral graphene 2D electron gas systems, there's a wide variety of states that we know um, from other condensed matter physics systems occur in this system under uh, variation of control parameters that can be varied, and some that have never been seen before. Uh, you're going to hear talks about, I think, probably all parts of this phase diagram today. On the right is rhombohedral graphene without a moire pattern, on not aligned to HBN. And what I'm going to talk about in the second part of my talk is going to be on the top right, just about some of these properties on the top right, where there's no more and there's no enhanced spin orbit coupling from a transition metal dichalcogenide. So I should have been there today, and I'm very eager to hear all the talks. But even though I hope everything will be all right, I haven't had a smooth last couple of days. This is the chatter from one of my group chats, which as you can see here, veered from its usual focus on Little League baseball statistics to what I should have done to recover my passport after I lost it on the weekend. So I still don't have a passport, but I hope I'm going to get one later in the week, and that everything will be fine indeed. But I do very much regret not being there and creating these technical difficulties with my talk. So most of my talk will be hopefully an introduction to the talks you'll hear later today about rhombohedral graphene. I'll try to, in the channeling Fred Prefect, I will try to point out some aspects of rhombohedral graphene that I think are relevant to the electronic properties that have been observed. Although, like his guide, not everything I say may turn out to be accurate. And the second part of my talk is I'll talk about some work being done in my group at UT Austin by Joe Roll, Toby Wolf, and Sparse Mishra. Generated by all of the mysteries around this. This is very much work in progress, and the particular thing I'm talking about is motivated by recent experiments by my colleague Leo Lee. This is Leo's version of the phase diagram uh, of rhombohedral graphene. This is a six-layer system. So in the many layer systems, um, this rough phase diagram, I think, is similar to what is being observed by everybody, but you'll hear more later today. And in particular, the most interesting thing, perhaps, are these superconducting phases. All of this part of the phase diagram is in a range of displacement field and density, where the system is, completely polarized magnet, All its spin and valley states are polarized, so it's quarter metal phase, and you see these chiral superconducting states. And so I'll return to that at the end of my talk, and in particular to these observations about what happens along the white line varying carrier density in this phase diagram, going through, the most interesting region when you turn on a magnetic field. Uh, and uh, and what you see there is uh, you see at low carrier densities, you see quantum Hall effects that I'll explain are, just ordinary weak fields, Shodnikov-DeHaas oscillations. But at higher carrier density, there are unusual quantum Hall effects where the Hall quantum number, Leo finds, is not equal to the filling factor. And nearby, there are states where the resistance drops to very low values at low temperature, apparently superconducting states. And yeah, that's what I'll talk about. So first part, and I'll be try to be mindful of the time, are just some observations about the electronic structure of this system and why it's so interesting and what aspects might be important. So everything is inherited from the, neat electronic properties of a single graphene sheet, where the relevant electronic degrees of freedom come from these blue pi bands, one band for um, one band for every carbon atom in the unit cell, and so uh, the important property, most important property of graphene is that, it's a honeycomb lattice of carbon atoms, and the splitting between the pi bands comes from hybridization between the different sublattices, and that hybridization vanishes by symmetry at the corners of the Brouin zone. And that's exactly where the Fermi energy lies. So in a neutral system. So so when you take that property and you add a displacement field and you make a multilayer, first of all, the neat thing that happens in rhombohedral stacking is that, so there's hybridization between layers, gamma 1 here, that doesn't vanish at the Brouin zone corners. And so these at the Brouin zone corner, the pattern of interlayer hybridization is that such that each carbon atom in the interior layers is hybridized to one other uh, carbon atom in a different layer, and that hybridization creates dimers that push these Fermi levels away from the Fermi energy. And so these states connected by the red lines are basically not present at low energies except as virtual excitations. So if you have rhombohedral graphene, then you have these two carbon atom sites which are basically decoupled from everything else, but still present at the Fermi energy. And so this gamma 1 is one energy scale. That's a high energy scale due to interlayer hybridization. And if you apply a displacement field, you can break the degeneracy between these isolated sites on the outside. And of course, by varying the density, you can change the hybridization within the layers at the Fermi energy, and that provides a third energy scale. And everything is based on the interplay of these energy scales. And so there's one thing I haven't said yet that I will emphasize in my talk, I believe is important, and that is that when I include perturbatively going away from k equals 0 and including perturbatively k equals 0 is at the Brouin zone corner, when I include perturbatively the hybridization within the layers, which is weak in that region of momentum space, then not only do I am I able to hop from, one sublattice to the other on the other side of the film, but I can the energies on each of these sites are renormalized in a k-dependent way. So right at the Brouin zone corner, these states are this dimer is split by gamma 1 and more than gamma 1 if there's a displacement field. And in the presence of a displacement field, there's the level of the pi electron on the isolated site is shifted by virtually hopping and hopping back. And at when the displacement field is zero, that effect cancels because there's level repulsion from the high energy dimer state and the low energy dimer state. But when the layers are, when a displacement field is plotted, these dimer states are polarized between the layers, and the two level repulsions don't cancel. And that ends up giving you a shift in the energy on a site, which is momentum, kind of ordinary band mass, which makes the energy of the conduction band uh, go down with K. And so those two effects are the most important effects in the band structure. And so if you look at some typical plot, and this plot is some band structure model many of you are familiar with, that also includes other smaller effects I haven't pointed to. And you can see here that the bands are very flat because they disperse, with a high power of K for many layers because of because it requires repeated hopping between the layers to get from one side to the other. But this on-site dispersion also starts to become important at larger displacement fields, and that the two effects sort of cancel against each other. That makes the bands even flatter. And importantly, it gives rise to these minima in the band structure at finite K. So the first states that are occupied in the region where most of the interesting states that are seen are actually at large K, not at small k. And I'll emphasize that as I go along. So, what I've talked about before so far with energy scales, if you change the density so that the hybridization within the layer is comparable to the other energy scales, that explains the density already on which all of these phenomena occur. So that's the backdrop of all of the ordered states that occur in this system. And now I want to, estimate or comment on some aspects that I think are important in these ordered states. Uh, First one is the role of the k-dependence of the block states. Every block state is a linear combination of many sublattice, many layers. And the geometry basically is how those sublattice spinners, defined by how those sublattice spinners change with momentum. And the point I want to make is that interactions don't like the sublattice spinners to change rapidly with momentum. Those because basically you can't make strong correlations, either quenched correlations in a ordered state or dynamic correlations that out of these states that have very different um, sublattice spinners at nearby momenta. And in the case of neutral bilayers, I'm not going to talk about this aspect of things. Maybe I think somebody probably will later today. But this effect leads to quantum anomalous Hall effect at neutrality that has we talked about a long time ago, but has been seen recently. And so that's one aspect that I think is important, and I'll say how a little later. Uh, another thing that's obviously the starting point for all of these phase diagrams is spontaneous spin polarization, and related to that, spontaneous valley polarization, which for the most part, seems to be sort of stoner magnetism, at least at low temperature. And but there are some notable discrepancies that I think probably have simple explanations, like in the in all of the mean field theories that were kind of with some adjustable parameters can sort of capture main features of the phase diagrams. You get these states in which three of the four available spin valley flavors are occupied, and these, for some reason, they never appear experimentally. That's always on my to-do list to explain that. So I mention it. And finally, the other thing I want to mention is the idea of momentum space condensation. And that is simply that that there is a tendency in mean field theory, and I think also, for quenched order described by mean field theory or fluctuating order, which can't necessarily capture in a mean field theory, there is a tendency to favor occupying states that are close together in momentum space because those states that are close together in momentum space have the strongest Coulomb matrix element, and there's most energy to gain from correlations. And yeah, and so this might be responsible for the some of the anisotropic states that are often seen in the system. Certainly in mean field calculations, it usually is. It's a mechanism that gives rise to a trigonal to a nematic order. And so this, it's an interesting historical note that, at least in my reading of the history, this idea goes back to incorrect papers by Fritz London about superconductivity. And he was somehow imagining that this tendency of electrons to group together in momentum space because of the long range of Coulomb interactions might be connected with superconductivity. Okay, I'm mindful of the time, so I'm going on here. And maybe I'll just mention this briefly. So, you know, it's very likely there's indirect evidence that density wave states occur in many parts of the phase diagram, and that these density wave states, um, you know, um, uh, uh, if um, if you had, if you had ordinary electronic states that didn't have these K-dependent sublattice spinners attached to them, then the favored density wave state, as we know from the ancient theory of the ordinary electron gas in a magnetic field, favors density waves with one electron per unit cell, so-called Wigner crystals. And those often occur, at least in mean field theories, in rhombohedral graphene. And this is an example calculation, but you don't necessarily get the order to be one electron per unit cell. And I'll come back to that again too. Um, okay. So let me see what I was going to say next here. Yeah. So uh, so uh, so that's my sort of unreliable guide to the galaxy of rhombohedral graphene. And for my remaining time, I'm going to concentrate on the ordered states that occur within the quarter metal state, and this is the original um, um, discovery of the phase space from Longju's 2025 Nature paper, where you can see these superconducting pockets already present. And so, um, motivated by the observations of Leo that I pointed to at the beginning, uh, it's tempting to try and understand um, what's going on in this system, starting from the magnetic field, starting from strongish magnetic fields, and then see if we can understand that, and maybe it'll tell us what's going on at weak field as well, because since they seem to be clearly connected continuously in the phase diagram. So that's what I'm going to talk about now. And what I'm showing here is on the left is a plot of the energy bands along some direction in two-dimensional momentum space for some displacement field. This is just non-interacting bands. And so uh, this shows the annulus that I pointed to before, and it's important that the depth of this annulus is controlled by displacement field. So, um, and this plot, which shows a one direction in momentum space and a minimum at finite momentum, and another direction in momentum space and a minimum at finite momentum. And so this actually emphasizes something I haven't said so far, that if you include more details of the band structure, then the energy depends on the direction of momentum. And this is showing the direction in which the annulus is deepest, and the direction in which the annular minimum in the bands is shallowest. And depending on the displacement field and the Fermi energy, you actually get separated little pockets uh, in momentum space at very low densities if the displacement field or when the displacement field is large. Okay, so that's a picture of the band structure I was talking about at zero field, and what happens to that when you have a large magnetic field. So the main thing that happens is that because the hybridization between the two low energy sites is goes like kx plus iky, which I should have emphasized earlier, which turns into a Landau level raising operator. You get these so-called anomalous Landau levels. And just as the energy, depends on k, not only through the k to the n coupling between the low energy sites, but from the on-site energies um, at zero field, in a magnetic field, the Landau levels, the energy of the states depends on Landau level index. And so you get a whole bunch of Landau level indices, but a very unusual pattern. The energy as a function of Landau level index initially goes down uh, with Landau level index before eventually screaming up. So the uh, um, so we can make so we're interested then in what happens with interactions when you have Landau levels like this. And I can say, in the experimental regime that I was pointing to before, the interaction energy scale is, roughly, let's say 30, 40 MeV. And this is a very blown up picture of the Landau levels. These are all separated by just a few MeV. So all of these Landau levels are, essentially degenerate as far as interactions are concerned. And and so we want to think about uh, what the consequences of that are. And together with Sparsh and Toby, we've been exploring models of that, which I think capture some aspects of what is seen in experiment. So the some details of the Landau level spectrum I just showed you depend on trigonal warping effects that I'm not including explicitly, at least in what I'm going to say. But so here's a bunch of Landau levels. The uh, um, first thing I'm going to show you is a Hilbert space truncated to three Landau levels with orbital indices 0, 1, and 2. And uh, and um, yeah, and the actual difference between these energies depends a lot on the displacement field. It can be tuned experimentally, and tends to be mostly in the region where the interesting physics occurs. The higher Landau levels tend to have lower energy. So here we're just looking at the phase diagram. These are, self-consistent Hartree-Fock mean field calculations. And the x-axis here is the energy difference between first Landau level and the zeroth Landau level. As I said, most of the interesting experimental region is on the left-hand side of this plot, of this phase diagram. And for the energy difference between 2 and 0, again, that's most of the experimentally relevant is below 0 here. And so in this calculation, we've actually, allowed translational symmetry to be broken to form triangular lattice states. But if there's only order at one of the or two of the six reciprocal lattice vectors, or only one direction in momentum space, you end up with stripe states. So those are also allowed in these calculations. And so the main thing that you find that is, I think, relevant to the experiment is that when the first Landau level is a little bit below the second Landau level, then even at filling factor 1, where if you didn't include very strong Landau level mixing, the ground state would be a uniform density, full Landau level state with no broken translational symmetry and Hall conductivity 1. The Hall conductivities of these states are indicated by the color code here. So, most of the phase diagram here, this is a nu equal 1 state where the Hall conductivity in E squared over H units equals the filling factor.
Allan,
But
5 minutes, please.
yeah, yeah. Uh, but uh, but when you're allowed to mix in the n equal 1 Landau level, you can form a more localized state. And even at filling factor 1, you can have basically what looks, if you look at a charge density profile, like an electron Wigner crystal state. And so this state has smaller Hall conductivity than the filling factor. And in this phase diagram, there are other interesting states that you can form when let's say it's E2 and E1 that are both less than E0, and but when they have nearly the same energy. you can break translational symmetry and get a charge density wave state where the Hall conductivity is bigger than the filling factor. And um, and yeah, so none of these states have actually been seen. I think that uh, the reentrant integer quantum Hall states I pointed to are related to this one. And so this is so obviously, if we let all of these Landau levels vary in energy in some arbitrary way, that gives a big Hilbert space to explore. These are calculations truncated to four Landau levels, and uh, the bottom set of curves, these are filling factor one, two, and three. Let me just talk about filling factor one to keep things brief. And so again, if the third Landau level is higher energy, then it's basically the phase diagram's unchanged. But as it becomes smaller, it starts to change. One thing I should have emphasized earlier is that in order to become active, the energies of the higher Landau level have to be lower because those electrons are basically fatter and harder to localize. So it's even at E2 equals zero, it doesn't change the phase diagram much, but then it starts to change it if it's negative. So it's a very, very rich phase diagram, but the general tendency is by mixing Landau levels, you can create new reorganized Landau levels that break translational symmetry and have a Hall conductivity that's different from their filling factor, usually less than their filling factor. And so in so the if I go back to Leo's data in a magnetic field, he sees these states. These left-hand side region, the Fermi level, is you can look at the data and understand from the patterns that these are basically high Landau level indices that are occupied here, and it's a regular Shodnikov to Haas pattern. But over here, as I increase the carrier density, I start to occupy the middle of the annulus. And once I do that, I want to put lots of electrons in there because of this momentum space condensation effect. And those electrons I put in there, which are, practically purely classical electrons because they're localized on a single sublattice and they have essentially zero kinetic energy. So, they want to localize as much as they can according to what region of momentum space they have. And so that's what I believe these reentrant integer quantum Hall states are in, revealed by a magnetic field. And probably, very similar states are present even without a magnetic field because for most part, this behavior can be traced as a function of magnetic field. And very nearby in Leo's experiments, there are low resistance states, superconducting states, let me call them, with zero Hall conductivity. And so it looks like, they're strange superconductors that are not suppressed by a magnetic field. And, once you break in time reversal symmetry, the reason for magnetic fields to suppress superconductivity is kind of lost. So maybe it's not a terrible surprise, but this superconductivity is actually strengthened by magnetic field. And quite possibly, as others have also imagined, this superconductivity is motivated by the collective modes of these nearby. nearby, either density wave states or quasi nearly quenched or nearly ordered density wave states at zero magnetic field. So that's an emerging picture. And so I hope this is here's the summary, and let me stop. And I hope this will be helpful for or useful introduction to the discussion that will go on today. And I'm very sorry that I'm going to get a new passport, and I'm going to miss it all. So thanks very much. I don't know if there's a mechanism for a discussion, but if not, then anybody can email me their comments, and hope to enjoy as much of the talks going on today as I can. Thanks.
Now we can possibly hear.
Here. Allan, we're going to have people ask you questions now.
But he's muted.
Okay.
I know he's.
Can you hear me?
Yes. Can you
Okay,
hear?
very good. Yeah, I can hear you.
Okay, very good.
Now question.
Questions. It's a,
So
it's a,
maybe I could even do this. I'm not sure.
everybody wants to ask question.
Okay.
Everybody's so afraid about technical details. So I'm
Hi, Allan, it's Adi. Do you hear me?
Yes, I do.
Okay. So you had this plot of the energy as a function of kx, which had two minima at unequal depth.
Yeah.
And you know the energy around the maximum. Are there Van Hoff singularities if I go from one minimum to the other?
Yeah, so there's in a non-interacting picture, as a function of Fermi energy. Originally you'll get little pockets near the deepest minima, and at some point those pockets coalesce into an annulus, and at that point there is a Van Hoff singularity in the non-interacting density of states. Yes.
And does it play any role in the calculations you showed? Does it have any effect?
Yeah, so I think not especially, and here's the argument that let's say a picture of hotspots in momentum space near Van Hove singularities is the right picture of systems in which interactions are generally weak, and but there are some small regions in momentum space where the velocity goes essentially to zero, and those regions become very important. And those are the Van Hove singularities. Here, that's not the situation here. The interaction energy scale is 10 times bigger than the entire band dispersion over the entire region of momentum space.
Thank
Thank
you.
you. Other questions?
Yeah.
Oops.
Oh, you-
Oh, yeah, there's one more. Okay, good. Let me quickly ask my question and then, yeah. Yeah, yeah. Okay, Alan, can you hear me?
Yeah.
Okay, great. Very quick question. Within your calculation, within Hartree-Fock, do you have a situation when density wave is order with finite momentum, presumably k minus k prime, is energetically favorable compared to q equal to 0 orders?
Yes, I think you're saying inter-valley coherence.
Yes. Mm-hmm.
Right. Yeah, so there definitely are maybe some regions in momentum space like that. What I was talking about, all of the observations that I was talking about toward the end of the talk is all in the quarter metal phase. So, really there's no experimental indication there that more than one valley is involved.
Okay.
So we focus mainly on that regime, which is complicated enough. So I've appealing to experiment to simplify the set of things you need to worry about. But certainly in the larger phase diagram, intervalley coherence order is a possibility.
Thank you.
Hi, Alan. This is Long Zhu from MIT.
Hi, Long.
Hi. Experimentally, we noticed that this so-called reentrant integer quantum Hall state, if you trace them back to zero magnetic field, they actually all those fans converge to a charge density that we think is corresponding to the charge density where we see the Wigner crystal. Can you comment on that?
Yeah, so that's that's a very attractive picture, and makes a lot of sense. And if so, the density wave states that occur in a magnetic field, and that in a magnetic field can give you, reentrant integer quantum Hall effects are telling you, something about what order is present, even at b equals 0. Yeah.
Thanks.
Yeah.
Any other questions?
Okay, I think we are done.
Thank you, Alan.
Yeah.
Thank you so
Okay.
much.
Yeah. Sorry. Wish I could be there.
Oh, I hope talk will be in person.
Should I use it?
So how would we
Just
do
use
in
it.
person those?
Who's sharing the sessions and you? Sharing the
We can tailor in Rhombohedral graphene.
Yes,
Okay.
thank you. Everything's good. Okay. Thanks to all the organizers for putting together this excellent workshop and for the opportunity to be here and tell you about what we've been doing in my group in collaboration with Josh Folk's group over the past year or so. In particular, looking at some of the experimental mysteries that have developed around superconductivity and rhombohedral graphene and ways in which it looks unusual. So we just learned from Allan that rhombohedral graphene has become a very nice platform for studying many different known phases of condensed matter physics and even previously unknown phases. The kind of key physics of this system is that the low energy electrons are polarized to these undimerized atoms on the top and bottom surface. So we can basically push all of the low energy states either to the top surface or bottom surface, or choice using an external electric field. And as we look at the band structure, as we add more and more layers in this metastable rhombohedral stacking configuration, we find that the density of states around the charge neutrality point becomes progressively larger and larger. Eventually, the density of state saturates due to trigonal warping effects and other features of the band structure. But it gives us a platform in which we can get, very, very flat bands in a crystalline system. And, this was known for a long time that it should be an interesting place to look. But as experimentalists, it took quite a long time to develop the machinery in order to find and isolate and make very high quality devices out of these metastable rhombohedral stack systems. And that's only come in the past few years, and that's now why we're seeing so many new experiments on these systems. This is some of the early work a few years ago in dual graphite-gated ABC trilayer rhombohedral. This is from Andrea Young's group, where they measure resistance as a function of doping and displacement field, the two operative degrees of freedom that we have access to experimentally. And what you see is basically that within these flat bands, there's a proclivity to spontaneous spin and valley polarization in a sort of generalized stoner instability that Allan talked about. So you'll see regions of quarter metals, half metals, unpolarized metals that you can access by changing the gate voltages. And importantly, what also often crops up is regions of sharply suppressed resistance that are indicative of very low temperature superconductivity, often at the boundary between two different isospin polarized phases or an isospin polarized and an unpolarized phase. Right, so right as there's a magnetic phase transition, then there's a decent chance that there'll be a low temperature superconducting state that arises. And so this is some of the kind of smoking gun evidence. You see a sharp suppression of the resistance to zero as you cool below a critical temperature. And there's many other checks that have been done, and everything looks consistent with 2D superconductors. This physics recurs as you change the number of layers. So as you go from a bilayer to trilayer, 4 layers, 5 layers, and so on, you generically see stripes in resistance signifying different isospin polarized phases with some probability of finding a superconducting phase at their boundary. Another aspect of the rhombohedral system that becomes especially important as you add more layers to the structure is what happens if you don't apply this large electric field to open a gap between the valence and the conduction band. So if you were here at this workshop last year, then you heard me introduce this concept of the band overlapped regime at low perpendicular displacement fields, where trigonal warping causes a large energy overlap of the valence and the conduction bands, such that there's a substantial region of parameter space over which you have both electron and hole-like Fermi pockets in the system. And because of this surface selectivity, even in an actual calculation, you find that these bands will segregate to opposite surfaces of the crystal. So, to pretty good approximation, the conduction band will live almost entirely on, say, the top surface, and the valence band almost entirely on the bottom surface, which you can flip depending on some small external displacement field that chooses which way they go. And some of the work that we've been doing in collaboration with Josh Folk's group at UBC is to look at 7 and 8 layer samples where these band overlapped regimes become quite prominent. I won't go through the evidence that we think is pretty compelling, that inside this black trajectory is where the system is described by having carriers on both surfaces. Outside is where you deplete one of the Fermi pockets and you just have carriers on either the top or bottom face of the crystal. But the interesting finding was that there's, this dual surface regime is littered with small pockets of sharply suppressed resistance that looks like 2D superconductivity. And so the way that we can characterize that in transport is to measure resistance as a function of gate voltage in either temperature or magnetic field, and see these characteristic domes in temperature or field where the resistance is sharply suppressed from the normal state below a critical temperature or critical out-of-plane field. This is not some fine-tuning of a specific layer number. We can go to a 7-layer sample here and even add a more A pattern by aligning to boron nitride. The details will change, but the property of seeing low resistance pockets that look like 2D superconductors generically along phase boundaries between different states of different metallic states of either polarized or unpolarized phases is quite general. And another surprising feature of these systems is that they actually like magnetic field in the plane of the graphene. So as we apply an in-plane magnetic field, these two little pockets that were initially connected by a resistive spike now are entirely an extended strip of a resistance dip. Okay, so if we just look at cuts in gate voltage, we can see that where we had a zero field dip, it remains a sharp dip and it just shifts in gate voltage. Where there was a spike, it becomes a dip. Right, so it looks like we're inducing superconducting correlations by an in-plane magnetic field. I'll skip the details of why we think this is, but essentially from quantum oscillations measurements, we can infer that on the right-hand side of this what I call a river of superconductivity, there's what appears to be a spin polarized half metal state. On the left, there appears to be an unpolarized state. And these low resistance states also far exceed the polyparamagnetic limit. So all of these things together suggest that we have a spin triplet, but valley unpolarized, or a valley singlet pairing mechanism that's responsible for this resistive dip. I've tried to be careful and not abuse language and call these superconducting correlations and not superconductor, for the reason that you can see the resistance is some value that's not zero, which kind of violates the most obvious property that you would expect to see in a superconductor in transport. And this is really a recurrent problem. We can look in these different samples and everywhere along this phase diagram and measure R versus T. And generically, we see things that look like superconductivity from their shape in R of T, but that the resistance will saturate and get stuck at some value that's not zero. It's not any universal number. Sometimes it's just a few ohms. Sometimes it's hundreds of ohms. But to the best of our ability to measure it, it's distinctly not zero. And this is despite the fact that if you make measurements of the differential resistance versus DC current in out-of-plane field, you can see oscillations in the differential resistance that are periodic in field that very sharply resemble Fraunhofer oscillations. So it implies that there's some sort of pairing and a phase coherence in the system that can give you these types of oscillations as a function of magnetic flux. And yet something in the system or something in our ability as experimentalists is precluding this from reaching true zero resistance. So we can start to look around in the literature and see that this is actually not a problem that's unique to the measurements that we're making. There's measurements of, say, bilayer graphene on WSE2, where you have what looks like a superconducting transition, but the resistance gets stuck just below 30 ohms. This is an ultra low critical temperature, and if you've ever tried to cool electrons to below 30 millikelvin, you'll know that it's not easy. So, maybe in this system, the electrons were just not getting cold enough. But we can look at other samples, and 5-layer sample, there's also a tendency for this not to be zero. A 6-layer sample, now with a much higher TC, the resistance in this sample is getting stuck at 100 ohms. A 13-layer sample, the resistance here is stuck at around 100 ohms. This is not to pick on anyone. These are just a few selective examples of a theme that's recurring, especially as these rhombohedral layers get thicker and thicker. It's common to see the resistance not go to zero. So we can ask, is this finite base temperature resistance really an experimental challenge that we're just, as a community, generically not able to cool the electrons enough? Is there some intrinsic feature of these states that's actually a real thing that's preventing it from going to zero? Or does the answer actually depend on the sample thickness and the particular state of interest? As I showed earlier, some of these really are true zero resistance states, and others seem not to be. So it's not obvious from this point what's going on. Many of you may know that there's actually a long history in thin film superconductivity of seeing resistance not go to zero despite having all the other hallmarks of superconductivity. And this was summarized in a Review of Modern Physics article in 2019 from my colleague Boris Spivak and Steve Kivelson and Aaron Kapitolnik, which they termed failed superconductors, or so-called anomalous metals. Things that look like superconductors, but they have a metallic state that appears to be the T equals zero ground state. This has just been appreciated, I would say, in the past few decades, but in a kind of re-examination of old work, it's been showing up for almost 40 years now. So this was work done by Allan Goldman's group here at Minnesota in thin film lead, where they could tune through a superconductor insulator transition by changing the thickness of the lead film. Right, so there's a pairing energy scale, and if the film is thick enough, then you get a zero resistance superconductor below TC. If it's too thin, then Cooper pairs localize, and you get a bosonic insulator. And there's this curious regime near the superconductor insulator transition where the resistance seems to become flat with temperature, but at a value that's not zero. And that's not a one-off observation. It's been showing up over and over and over again across a wide variety of different quasi-2D superconductors. So this is more recent work from Allan Goldman's group here, where they're now looking at thin film cuprates and using gate voltages to tune through the superconductor insulator transition. And again, they see an instance where there's a regime of gate voltages over which there seems to be a metallic looking state in between the superconductor insulator transition. You can make engineered systems, so Josephson junction arrays. Here's work from Nadia Mason's group of niobium islands on a gold substrate, where again, they seem to see a 0 temperature metallic state. That is a challenge to theory to understand. Of course, one must also be very careful because there are known reasons why a true superconductor can mimic this so-called anomalous metal. So here's work from Danny Shahar's group that shows that whether you look at amorphous thin film superconductors or crystalline 2D superconductors, just as examples, if you don't properly have good low temperature filtering in your DC lines doing transport, then microwave photons can come in and generate Bogoliubov excitations that will heat the system as they relax. And without filtering, the just empirical observation is that you can get an apparent T0 metallic state. When they add the filters, then you get a proper activated superconducting state that shows up. So there are known extrinsic mechanisms why this type of behavior can happen. But the kind of useful thing about these gate-tunable superconductors is that we can start to use them as built-in thermometers in the system. So here I'm going back to the 8-layer sample and zooming in on a region with 3 different pockets of low resistance state. And again, these are the ones that we can characterize as domes in temperature and magnetic field. And the kind of curious thing that we see is that this central pocket, which has the highest onset temperature, its resistance appears to saturate at a temperature above which its neighbor develops this sharp resistive drop. So in a naive picture where any external radiation that we haven't properly filtered out is heating the system, it's now becoming difficult to understand why, if the effective temperature is set at, say, 70 millikelvin, how another state could develop at an even lower temperature scale than that. So it's not proof of anything, but it's kind of a curious observation that's a little bit difficult to explain. So, we continued to look into this somewhat by accident. We were trying to do something else, but, we continued our collaboration with Josh Folk's group. So this is a device that I'll be telling you about for the rest of my talk that was made and measured primarily by my students, Anna and Abigail, with support from my other students, Manish and Derek, in the fridges of Josh Folk's group at UBC, where he spent a long time making sure that, electron temperature is really as low as possible and we can make ultra quiet measurements. So separately, they've calibrated electron temperature to be something like 25 millikelvin at the highest, maybe even lower. And this is also in collaboration with his master's students, Tobias and Reveal. Okay, so the new sample geometry that we're looking at is the same 8-layer rhombohedral, but now with a monolayer of tungsten diselenide as a substrate. The idea was to try to understand the impact of induced spin-orbit coupling. I don't have anything meaningful to say about that for the moment, besides the fact that what it empirically does is allow you to see additional low resistance pockets without the use of an in-plane magnetic field. So they're all still showing up along the kind of familiar trajectory in gate space where we previously saw the field-induced river. But now we don't need a magnetic field to see them in some of the regions where we previously had without the WSE2. And the kind of curious finding here is that this low resistance pocket corresponds to a proper 0 resistance superconducting state. So within our measurement noise floor of about 1 ohm, we see true 0. So this is in RxX, we also see 0 in RxY, which I'll show you later, with the transition temperature of just below 50 millikelvin. But curiously, if we look at this pocket of another low resistance state, it has a higher transition temperature of about 125 millikelvin, and yet its resistance seems to get stuck at about 8 ohms, which is a non-universal value. It's just what it happens to be in this particular measurement that we did. But once it gets stuck, we can cool by over an order of magnitude in temperature, and it has no temperature dependence that we can detect at all. So we can do all of the checks that transport allows us to make sure that these things otherwise look like superconductors. The one with true 0 resistance has a dome in RFT, some dome in resistance versus out of plane field. If we measure differential resistance versus DC current, there's a critical current, which generally decreases with out of plane field, although in a strange fashion, which I'll come back to in a moment. But all of these look like kind of canonical, weak 2D superconductivity. The same is true for this pocket, dome in RFT, dome in RFB, diamond shape. in differential resistance versus DC current and out of plane field. Everything about this also looks like 2D superconductivity, except for the fact that it's not zero resistance below any of these critical values of temperature, field, or current. So let me just take a moment as an aside to explain why the superconductor's differential resistance looks weird. Well, I can't really explain why, but I can at least explain more of what. So if we really zero out the in-plane field and then measure differential resistance as a function of out-of-plane field, we see that there's a clear hysteresis with the sweeping direction of field. Okay, so there's a zero resistance state in longitudinal and Hall resistance that is history dependent on how we sweep the field. And we can suppress that hysteresis by applying some tens of millitesla of in-plane field. So this seems to be related to some sort of domain wall behavior and possibly related to orbital magnetism, but we don't know yet. But we know that that hysteresis goes away with some small in-plane field, which will become relevant for what I'll say next. Okay, so the kind of magic of this system is that we can use an in-plane field to induce superconductivity everywhere along this resistive bump-like feature, or at least that's what we learned in the 7-layer sample without the WSE2. And it turns out if we try that same measurement, so we apply 100 millitesla or 350 millitesla of in-plane field, indeed, this entire region fills in with a low resistance state. But now, especially if you look at the 350 millitesla measurement, you can find that where it was zero resistance, it remains zero resistance. Where it was finite resistance, it remains finite resistance. And they seem to form a sharp boundary between the two, as if they're distinct phases of the system. So this shows up clearly in line cuts. I can take a line cut here or down here. So the one up here crosses from a half metal metallic state to a zero resistance superconductor, and then takes a sharp step to this 8-ohm dissipative state, and then back to a normal metal. Whereas if I look down here, it basically is just getting stuck at this 8-ohm dissipative state the entire way. This really shows up clearly in measurements of resistance versus temperature. Right, so I'll take cuts here, here, or here, and show R versus T along those gate cuts. So this one is D, this one is F, this one is H. So the D is the most striking. You can see that there's a dome of zero resistance state that's neighbored by a separate dome of a lower resistance state than the metallic normal state surrounding it. And you can either transition directly into the zero resistance state, you can transition directly into this finite resistance state, or you can even take a step from one to the other. And then as you go further down towards 1 volt in the top gate, eventually you transition to getting rid of the zero resistance state and just having the dissipative pocket remaining. It gets really strange looking if you start to measure as a function of the DC current. So here's differential resistance versus the same trajectory and gate space as this map versus DC current. So again, the half metal, the unpolarized metal, the zero resistance pocket. And if we were to take a cut here just through the zero resistance pocket, that's the insets, it looks like standard superconductivity, where you have zero differential resistance and a spike for the critical current and then some normal state. And you can integrate to look at IV, and it looks like a textbook superconducting IV. But if you look over here at minus 3.2 volts on the gate, then you also see what looks like a critical current that decreases to zero at the critical temperature. But everything underneath that critical current is dissipative, right? So at zero bias, you have some finite dissipation. And then perhaps even most bizarrely, the differential resistance actually drops to zero before it hits the critical current and enters the normal state. Then lastly, you could fine tune the system to the point where the two pockets are sitting on top of each other in gate space. And then you find that these behaviors coexist. You have this inner dome of a zero resistance state. You use enough critical current to go through a criticality, and then you enter an outer dome of this dissipative anomalous metal state before you then hit a second critical current and then recover the ohmic normal state beyond that.
The colors are just different fields or different temperatures?
There's a lot of colors, sorry.
Sorry, on the rightmost.
These are different temperatures. They correspond to these cuts. So this is just above TC. This one is near base temperature, and this one is somewhere between. We can integrate these if you prefer to look at it in IV. Okay, so this one has a kind of a strange IV where its voltage is 0 until you reach the first critical current, and then it takes a step, and then it kind of gets stuck again, and then it finally takes another jump and then enters the ohmic normal state. Whereas for the anomalous metal, it's actually ohmic at low driving current, and then flattens out and then takes a huge jump to the ohmic normal state at large DC current. We can try to look at this within the BKT framework. So the zero resistance state, if you look at IV on a log-log scale as a function of temperature, indeed, it properly goes through the voltage proportional to I cubed BKT transition. And so that's in the inset. Alpha is 1 at high temperature, and then it just shoots up as we cool down to base temperature. And that sets a BKT temperature for this particular case of around 60 millikelvin. But if we try to do the same thing in this anomalous metal pocket, it's as if the system is trying to surpass the BKT criteria, but then ultimately fails. And the low driving current fate of the system is to be roughly ohmic. The last thing I'll show you is what happens as a function of magnetic field in the out-of-plane and in-plane directions. So if we go to one of these conditions, like here, where the two states are sitting right next to each other, and measure differential resistance as a function of DC current and out-of-plane field, you see that the primary feature is this big diamond that's associated with this dissipative anomalous metal state. And then there's a little blip at the center. And if we zoom in, we can see that that blip is a real thing. It corresponds to a second little diamond that's associated with the critical current that destroys the zero resistance superconducting state. We can take a gate cut and measure resistance versus out-of-plane field, now on a log scale of field, because the characteristic fields are generally separated by about an order of magnitude. And we can see that there's a zero resistance dome that's kind of ensheathed by this dissipative dome surrounded by the normal state. Okay, so if you were to think about it just at this gate voltage, then maybe there's nothing too strange. You would say, okay, there's a zero resistance state that gets driven by magnetic field into a dissipative state before it reaches the normal state. And it's well known that out-of-plane field can generate vortices that can depend and in this flux flow liquid regime lead to dissipation. But what it forces us to contend with is that that dissipative state seems to be smoothly connected to zero magnetic field, where at zero temperature, there's no reason to expect that you should have unbound vortices. There's a similar separation of field scales with the in-plane field. So the superconductor generically survives to about 1/4 or 1/5 the total field of the anomalous metal. But both of these strongly, like order of magnitude, exceed the polyparamagnetic limit. Okay, so this in particular, I think, points away from a model in which you would have a percolative network of superconductor and normal metal, because you would not expect that such a scenario could generate a critical field that's order of magnitude larger than the superconductor itself. Or if you take a superconductor and then you embed it in a bunch of metal, there's no obvious way in which that would boost the out-of-plane critical field. So the conclusion from this is that the anomalous metal is apparently not just simply some disordered version of the superconductor, but something else entirely. So of course, we want to try to think carefully through what are the extrinsic reasons, the kind of boring reasons why such a thing could happen. And these are what we came up with. And as I'll show you, I think we can more or less rule all of them out. So one is that we're somehow just not cooling the electrons enough. Another is that we have bad contacts or common mode voltages that are developing. Another is that we have random spatial disorder, like a effective Josephson junction array. And the last is that we have normal state that forms a series resistors with the superconductor, like spontaneous S&S junctions. So I'll come back to this temperature map and point out that the critical temperatures of these two phases are very similar. So naively, that points to having a similar energy scale for pairing of both of these states. And that also points away from this anomalous metal just being some sort of superconducting state that's suppressed by external noise or heating. Because again, naively, the superconducting pocket should act as an internal thermometer. If it's affected by external radiation, this one with similar pairing scale should be as well. Of course, there's a way out of this, and you could assume that there's some new low energy scale of the system that is super sensitive to noise associated with this region, but not this region. But then that requires that you define what that scale is. And at this point, I think that's an open question. And certainly if anyone has any ideas, it would be interesting to discuss. Another question is the contacts. In our devices, our channel is dual graphite gated, but we have some of the region of graphene hanging out that we can dope with the silicon global backgate that acts as a tunable contact. And we can look at the nature of these states as we change the silicon gate voltage to change the nature of the contact. And what we find is that if we make the contact insulating, then we can make the whole thing fail. But otherwise, basically, no matter how we dope the contacts, we always get the same answer. It's not an obvious contact problem. We've also looked at different pairs of contacts here and here and here, different regions of the Hall bar, different sides of the sample. So those measurements are here, here, and here in these three columns, and they're just a representative set of measurements. But you can see that everything is really like identical, even down to almost quantitative details. We've also made an entirely separate device, separate flakes, separate chip, everything different. I'm going to show you a comparison. These are just a representative subset of the measurements. The second device is evidently more disordered. So there's something a little bit wrong with it. But all of the kind of key footprints of these features in parameter space are reproduced. So for instance, just look at this versus this. You see the same hook-like feature with the zero resistance state neighboring a dissipative state. And if you take line cuts, they really look the same. And so you can judge for yourself how similar these other things are. But to the best of our ability to judge, these things look highly reproducible. The last possibility is that you somehow get this scenario to spontaneously form. You have some strip of normal state interrupting the superconductor across the voltage probes to form S and S junctions. This seems unlikely to happen between all voltage pairs and multiple devices that we make. But also, the induced normal state proximity length should go as VF over T in the clean limit or over 1 over square root of T in the dirty limit. And in either case, as you cool the temperature to 0, you would expect that these things would eventually Josephson couple and recover zero resistance, which we don't see. Okay, so this is what we've thought of so far, and certainly we're open to other kind of mundane possibilities, but we can't think of any more. So if we start to think about what are the potential intrinsic mechanisms, one possibility is that we have pairs that are fluctuating in and out of existence. So there would be no well-defined pairing amplitude or gap, and we only have superconducting correlations. It's in some sense akin to this like paraconductivity regime just above TC in standard superconductors. Another possibility is that pairs have a gap, but the phase doesn't order. So there's essentially zero stiffness, and this is the limit of a failed condensate. And the third is that pairs exist and they condense, but for some reason, vortices, as a topological entity in the BKT sense, remain unbound down to 0 temperature and then can freely proliferate and lead to dissipation. But again, it's not obvious why that should happen. The kind of last thing I'll point to is, some parallels to what's been seen in other so-called anomalous metal systems near the superconducting insulating transition. There's a quantum phase transition. So this is work from Charlie Marcus's group that's been ongoing over the past decade using aluminum indium arsenide superconductor semiconductor systems as gate-tunable Josephson junction arrays. And what they find is that they can indeed gate tune through an SIT, but that you often see this extended region of apparently metallic state at around resistivity of H over 4E squared. And that number is thought to be meaningful because it's predicted to be the Cooper pair quantum of resistance. Okay. And so previous attempts to explain what this anomalous metal have been within a Caldera-Leggett framework, where you think about coupling to some sort of, say, quantum fluctuations of an electromagnetic bath. And if the coupling is not too strong, then those quantum fluctuations can stabilize a metallic state down to 0 temperature. The situation in graphene is a little bit different. So again, what we see is that there's a saturation of resistance over a decade change in temperature below the critical temperature. And that's hard for thermal excitations to explain because you would naively expect that those should look activated and that you would not get 0 DRDT. They're also challenging for these Caldera-Leggett type explanations because the normal state conductivity is around 1,000 E squared over H. And that's where you should have strong coupling to the bath and strong damping. So there's no obvious reason why the phase wouldn't just get fully locked across the sample. One thing I'll point out is that if we look back at our state and do Landau fans and take the FFT, what we find is that on the left-hand side, the dominant frequency is at 1/4, suggesting an unpolarized metal. On the right-hand side, it's at 1/2, suggesting a symmetry broken state, which we think is a spin polarized state, not valid due to the lack of anomalous Hall effect. So the observations are that both of these superconductor anomalous metal exceed the polyparamagnetic limit, but the superconductor is generally on the spin polarized side and the anomalous metal is generally on the unpolarized side. And generically, these things lie at the boundary of a magnetic phase transition where, the relevant isospin modes are soft. So I don't have any sharp ideas, but it's, I think maybe interesting to think about whether quantum fluctuations of some other degree of freedom, like spin, could play the role of could induce the necessary dissipation. Okay, so the summary is that we see similar onset temperatures of these two phases that look like paired phases, but have very different, zero temperature fates. The normal state conductivity is huge, where standard theories so far would predict robust superconductivity. In this anomalous metal state, the resistance only drops by, a small amount, like factor of 4, 5, or 10 at most. There's very strange non-monotonic DC current responses, but these phases are very sharply defined in gate space, and they're broadly reproducible across different contacts and in different devices. All right, so with that, let me again thank my entire group as a long-term effort to get to this point, especially the students that I highlighted before, and also the years-long collaboration that we've had with Josh Folk's group to do these measurements. And thanks for your attention.
Thanks. Oh, great talk, first of all. Thanks. Have you seen any variability in time-dependent effects?
Okay, yes, we have, but that goes away when we apply an in-plane magnetic field. So everything that I've shown you here is stable in time. But the measurements that I showed you that had those hysteresis behaviors with out-of-plane field, those are not stable in time. There's been similar observations from recent work from Ellie and Wang.
Characteristic time scale of switching between?
That depends on that. There's no universal answer to that. It can be minutes.
So wonderful. So I have a question. So you basically you have surface superconductivity, top layer, bottom layer, and in between you don't. So is there a possibility which you can eliminate that there's some Josephson stuff coming from this?
That's a great question. So I have two things to point out about that. Let me try to get back to, okay. So one is, okay, the real answer is that I don't know about the Josephson coupling between layers, but the way that we can kind of get around it is to also see that the behavior happens even in regions where it looks like we fully depleted one surface and everything is just happening. There's no dual surfaces anymore. Like this physics just kind of doesn't care about whether you have the other surface populated or not. It seems to be a perturbation and not something fundamental, which we can assess basically from whether features are vertical or diagonal in these two gate maps. Right? If they're diagonal, then it's a single 2-deg that's coupled to both gates. If they're vertical, then there's some sort of screening from the gates because you have charges on both surfaces. The physics doesn't seem to care about which you can see that it just kind of persists across this hook. So if there is some effect of coupling to the other layer, then I don't know. But even if only one layer is superconducting and the other is metallic, like naively, you should still shunt out the resistive surface with the superconductor.
That would slightly depend on how you touch contacts, right?
Our contacts are, so we etch through the entire structure and then we make side contacts so they touch all the layers.
More questions?
Yeah, so this comparison between the two devices, maybe is it okay to say that seems like disorder enhances me more this quasi superconductor, let's say, than the usual superconductor?
I think the footprints of the two are basically the same between the two devices. So what disorder can do is provide another reason why a true zero resistance state might fail to achieve zero resistance. Like that for sure can happen. Or if you have a disordered device, even if you're supposed to have a true zero resistance state, then you can see that it doesn't actually get to zero. What we tend to find in that case is that the temperature dependence is not flat. Like the resistance will continue to decrease as we cool the system down is if more domains are Josephson coupling with cooling. But I guess what I want to try to point out directly is that if you look in the cleaner device, there's like this pocket and this pocket. In the Dorrier device, you can see the outlines of those pockets, but things get kind of strange in ways that are not easy to directly understand.
So, but do you think then this quasi superconductor there would not require disorder? It would be there if it was clean in some sense.
What I would say is basically this is as clean and homogeneous as we've ever seen in a strongly correlated crystalline system. So this is the best we can do to get rid of that and answer that question. I can never promise that there's no disorder, so I don't know, but that's what we have so far.
Is there any dependence on the orientation of the in-plane field?
We've looked at this and we don't see anything obvious. If it is, it's super tiny effect.
Let me ask one question at the very end, going back to the very beginning, zero the question. So your superconductivity is at the boundary between full metal and half metal.
Yes.
If you go above, it is the onset of superconductivity. Is the state half metal or full metal?
In temperature?
Yeah.
Okay. It depends on, everything in Rhombohedral is complicated, so the answer is always it depends. But yes, but in this case, these jumps I think are related to some instability of a many-body phase. So to the best of our understanding, the parent phase is already isospin polarized, and then you develop superconductor as the daughter of that. They don't co-develop.
Yeah, and then the other one?
This one?
Yeah.
Harder to say. I think it's a little bit hard to assess in transport, but I think it's actually on the unpolarized side of the transition. So the parent state may be unpolarized.
Can it be that the difference is that one is inside that ordered state and the other is in the formative state? Or you cannot think that?
I think that it's not unreasonable to think that's true. Yeah. How it leads to the outcome, I don't know, but that might be a fine starting point. Yeah.
Okay. With this, thanks very much. For the delay with the start. Coffee break will be half an hour. We'll just reduce the time for lunch. So we'll see here in half an hour.
So I think it's the charts. You're going up or? Yes. Okay.
I guess we thought we these are more serious things than
Are you sitting here?
Oh, sorry. It's sorry. Yeah. Okay.
One of this. Don't have this
Oh yeah. Like 1 hour.
Let's continue. Martin Ledwith and Dirac Trions in with the Bilayer Graphene and the small asteroid expansion.
Hi everyone. I want to talk to you about some work I've been pretty excited about over the past couple of years. It started off trying to understand some things in Bilayer Graphene, but grew into trying to develop a new theoretical tool that we're pretty excited about. So I think probably the first 2/3 of the talk I'm going to focus on is just the Bilayer Graphene stuff, and last 1/3 I'll talk about this new theoretical tool. I think there are going to be some other talks today about pretty related things, and so I tried to orthogonalize slightly, and I'll also try to pull out some connections. Oh, if possible, but no big deal. You can just use that one. This is a. This problem initially got me interested. Microphone. Thanks. Is this good now? Better?
Yeah.
Okay.
That's right. Yeah.
Okay, great. Right. So I want to start kind of with a broad overview of two really kind of paradigmatically different areas of strongly correlated physics. On the left, I have a cartoon of a Mott insulator where charges kind of localize at each side of the lattice. And because the wave functions don't overlap very much, the spins essentially remain decoupled. And this gives us a very strongly correlated insulator that's very far from band theory, but also a pretty simple state because we can understand it very classically, where the charge freezes out and the spins are fluctuating. So the charge freezes out and we get a single local moment at every site with approximately zero direct exchange. And then a lot of the famous physics associated with, that's believed to be associated with high temperature superconductivity and so forth, comes from doping these systems or coupling them to dispersive electrons. And I want to contrast that with another area of strongly correlated physics, which is quantum Hall physics. And here there's a lot of differences. The band is topological, so there's no way to write down a basis of localized states. And also the charge density is homogeneous. So instead of having peaks at every lattice site, charge is like totally smeared out. And in the system, there's all sorts of interesting things that happen. But it all comes from the Coulomb interaction projected to these very interesting topological bands where wave functions have to be delocalized. And on the spin side, it's usually associated with direct exchange and very strong ferromagnetism. And so these systems are very different microscopically. Their phenomenology is also quite different. But I want to kind of ask if we can try to bridge these pictures a bit and see what interesting things can happen. In particular, I want to ask the question, is it possible to get kind of the hierarchy of scales that you associate with the Mott insulator, where charge degrees of freedom have a much higher energy scale than spin? Is it possible to get this hierarchy of scales in a system with band topology? And there are various reasons why one might think this would be interesting. For example, spin textures and topological bands bind electric charge. And so we want to ask if this is possible, because from a lambda level perspective, one might be a bit pessimistic, but it turns out it is. And then what happens in it if you try to do this? And this is pretty strongly motivated from phenomenology in twisted bilayer graphene, where so twisted bilayer graphene is two layers of graphene twisted at a small angle. You get pretty narrow bands close to zero energy, and you have 2 bands per spin per valley, so a total of 8 flat bands. The number 8 won't be really important in my talk, so if you want, most of my talk is understandable if you just think of a single topological band that has spin. And there are there are kind of there's tons of experiments by now, and I'm showing some selected ones here. And they kind of fall in different camps. Some of them motivate a Hubbard picture, i.e. having a concentrated charge density at the AA site, superconductivity in Mott insulators, but also quantum Hall type phenomenology of integer and fractional return insulators. But the two that feel particularly discordant is that there's a large entropy at very low temperature consistent with having decoupled moments at each one of these AA sites. But at the same time, from both theory and experiment, we have a lot of reason to believe that these bands are topological. So before I move on, I want to point out that there are kind of 2 different approaches to studying this system. One is based on believing that all the interesting physics is in the flat bands. So this remote band gap, lowercase gamma, is much larger than the interaction scale U. And the other hierarchy of scales is where the interaction scale is much larger than this band gap to the remote bands. And on the right, there's so in the left, you just want to project out the remote bands and focus on the flat bands. In that case, there are really no local moments in the Hilbert space. These bands are topological. There's another approach where you involve the remote bands, after like a lot of really pioneering work, and especially codified in this heavy fermion model by Jida Song and Andre Bernevig,
they argued that in this limit, one should expect heavy fermion physics because out of most of the flat bands and then some of the remote bands, you can make localized F electrons. And in that case, this gamma turns out to be the bare hybridization between the C and F electrons. And we'll hear talks associated with the model that was initially used to describe this regime. But I want to point out, and I think maybe those talks will point out too, the model can describe both of these regimes, but the physics in each of these regimes can be quite different. And so for this talk, I want to focus on the hierarchy of scales associated with the left regime. And one could describe this either by projecting to the flat bands or by studying this Song-Bernevig model and then taking this limit at the end. So I'm going to do this, and I think some future talks will work with the model that was initially motivated by this, but can also be applied to this limit. And one of the reasons I want to focus on this is that in addition to describing twisted bilayer graphene, I also want to talk about the conceptual aspects associated with having Mott-like physics in topological bands. And those conceptual aspects are a bit cleaner if we really just project to topological, isolated topological band. Okay, are there any questions at this stage? Okay, great. So the perspective I'm going to take is to take the band topology of these bands seriously, but also to take two kind of geometric or quantitative features of these bands more seriously as well, which is that the charge density is concentrated at these AA sites, and also the Berry curvature in momentum space is concentrated around k equals 0, or the gamma point. And it turns out that one can make some arguments to say that these are related. If you take a model of a topological band with concentrated charge density, there's a saddle point approximation you can make around each one of these AA sites. And that gives you wave functions that look like this, where in most of the Brillouin zone, it looks like localized states associated with these AA sites, i.e. block waves of these localized states, like Gaussians at each one of these AA sites. But then the topological obstruction bites you at the gamma point, where the wave function is forced to be orthogonal to this, like the Wannier state that you want to make localized at the AA site. So in almost all the Brillouin zone, the band looks topologically trivial, looks strongly localized. But in a small region around the gamma point, there are wave functions that are orthogonal to the localized ones. And the Berry curvature is concentrated around this region. And I think this makes kind of an interesting problem. One, like in some sense, there are very few electrons here, so one might think that they don't affect the physics too much. But on the other hand, they are responsible for the band topology and give you an anomalous Hall conductance, for example, if you fill one of these Chern bands and not the other. So what I'm going to do is I'm going to project Coulomb interactions to the wave functions that describe these bands. We can also compare these wave functions very explicitly to the twisted bilayer graphene wave functions, and we find good quantitative agreement when this small parameter s squared in appropriate units is around 5%. And yeah, there are also I've kind of written down these wave functions here, and I haven't really told you too much about where they come from, and that's because they come from, you can motivate them from many different perspectives. I talked about the saddle point approximation. You can also get them from taking a Dirac particle in an inhomogeneous magnetic field, and that's particularly useful for connecting to quantum Hall physics quantitatively. Also, you can take the Song-Bernevig heavy fermion model and project to the flat bands, and you get very similar wave functions. So yeah, I'm going to be projecting Coulomb interactions to this band and using this s squared as a small parameter.
So in this limit of Dirac, is it just like solenoids, or what is the picture?
No, there's a negative magnetic field as well too. It's you take a homogeneous field and then you add like a cosine to the field, and then you increase the coefficient of the cosine. But it'll have negative magnetic field as well, but the average will be 2 pi. And it's not so crazy because in these moire materials, you can get like layer space fermions, and those can give you positive and negative fields. So I kind of want to summarize a bit how to think about this, this setup. It turns out there are kind of there's an emergent energy scale associated with a small parameter s squared, basically associated with the fact that very few electrons are in this region. And it turns out one can show that this leads to some energy scale of order US squared. And the intuition for this is that the small space of electrons just can't contribute that much to bulk thermodynamic quantities. Things like energy, entropy, things that are dominated by things that are kind of extensive in the number of electrons in the system. So all of these things that scale with the number of electrons are kind of dominated by the region that's away from this gamma point, and this just can't affect the energetics too much. So these contribute an energy scale of order US squared, and if temperature is much bigger than this US squared, then the entropy that you would get if you imagined this to be a trivial band, there just aren't enough electrons to quench that entropy. And there's a way to understand this in real space as well by taking Wannier states associated with this band. And Wannier states in Chern bands are normally thought to be pretty hard to work with because they have power law tails and are very extended. But it turns out with this small s parameter, the overlaps between these very long tail Wannier states are very small. But I'm not going to talk about this bulk thermodynamics too much, but you maybe trust me that if you do things carefully, you can reproduce the bulk thermodynamics associated with the kind of thermal Hubbard model, except without any localized states. But I'm really going to focus on quantities where the small k-space region really enters, because for these quantities, you can see both topology and local Hubbard interactions kind of intertwine. And specifically, I want to focus on momentum resolved spectra, where we really can directly probe this region. And so I'm going to do this with the electron spectral function. And I've kind of provocatively put up this picture of cuprate Fermi arcs to kind of illustrate that, this in strongly correlated materials, the electron spectral function is one of the first things that one should look at, because it's kind of gives you a window in how the low energy carriers of the system behave. Are they similar to non-interacting electrons? Are they heavily dressed? Are there weird anomalies? This has been a source of confusion in the cuprates for a long time, and I think we're finally entering a regime, both theoretically and experimentally, where we can ask similar questions in more array materials like twisted bilayer graphene. So we calculated the electron spectral function with the small parameter, and we got something pretty funny. It looks like a Mott insulator in most of the Berlin zone. So here there's an upper Mott band, here there's a lower Mott band. But then as you go to k equals 0, you get a linear crossing. And we call this a Mott semi-metal because it's very Mott-like. The Green's function looks very formally similar to that of a Mott insulator everywhere besides the gamma point. And at the gamma point, there's this linear crossing. And something even weirder happens when we add a dispersion. So we have this h of k sub nk and sub k. This isn't the most realistic dispersion for TBG, but I want to kind of use it to illustrate a conceptual point. Similar things happen for the realistic dispersion. You actually open up a gap for this point, but it's a really weird gap. All the electron spectral weight is up here. And on the other side, there's a gap in the spectrum. And on the other side, there's 0 quasi-particle residue. So if you sit in this gap and you try to dope the valence band, it's very unclear what you're doping. There's no overlap between this excitation and the electron.
Are the 0 temperature results or finite temperature?
Yeah, good question. So you assume the temperature is inside this regime, and then the result is temperature independent. It will not hold true down here. So there's a wide regime in which these results will be temperature independent. And then
when you say that the spectral weight is 0, is it exact 0 or something very small?
Good question. So there's a sense in which it's exactly 0. And it doesn't depend on small s.
So what is the sense in which it is exactly 0?
Yeah. So we can find out exactly what excitation this corresponds to. And we called it a Dirac trion. And the word trion is because it's a 3-particle excitation. It's made out of 2 electrons and 1 hole. And you can think of it as like a density wave bound to an electron, but very tightly bound. So it has all the same quantum numbers as an electron at a generic point in momentum space. It has the same type of flavor quantum number, has the same charge. But at the gamma point, it turns out to have it has different quantum numbers under all the rotation or crystalline symmetries. So at the gamma point, it's enforced to be orthogonal to the electron. So if this excitation has spectral weight in the system, it will create something that is exactly orthogonal to the electron. And that orthogonality you can either view as being symmetry protected or protected by the band topology. So that's the sense in which the residue is exactly zero here. Maybe like it might not be exactly zero in the sense that if there's some broadening, this could bleed over here. But there is an excitation here that's exactly orthogonal to the electron. And in that sense, the residue is zero.
Not in the other band, right? So there could be a different orbital that has the right symmetry to mix with this.
Oh, yeah, that's a really good point. So if you go to the heavy fermion hierarchy of scales, so like the opposite hierarchy of scales, then this trion excitation can mix with the remote bands. So this relies on the topology of the flat band Hilbert space. Once you add more orbitals, that goes away. And for the parameter, this should be like on the order of a 5%, 10% mixing. Yeah, that's a really good point. So this relies on having only topological bands at low energy. I think one pretty fun thing about this is that this excitation, it's made out of 3 very heavy particles, actually. So it corresponds to, if you expand this out in momentum space, it's possible to convince yourself that only the states far away from the gamma point contribute to it. Gamma point excitations don't contribute to this excitation. And as a result, it's really made out of 3 really heavy things, like 2 heavy electrons and 1 heavy hole. But nonetheless, this excitation is arbitrarily light. And the way it works out is that away from the gamma point, this thing is hybridizing with the heavy electrons that are very localized. But at the gamma point, there aren't any of these heavy localized electrons for it to hybridize with. And so it's forced to go down to 0 energy. And yeah, another thing is if we do all it turns out if you do all the bells and whistles, you can show that it's a carrier. If we like do the realistic TBG spectral function, which I'll show in a couple slides, one can argue that it's actually the carrier in the superconducting normal state. And so we believe that these things could be useful for understanding pairing in the system. And I want to briefly talk about some experiments really impressive experiments from Shahar Alani's group, where they were able to measure the spectral function in twisted bilayer graphene by using this thing called a quantum twisting microscope. They basically take a layer of graphene on top of TBG and twist it relative to TBG, and they get momentum resolved tunneling through that. And as you tune the twist angle, you go through a line cut in the Moiré-Brillouin zone. So over here is the gamma point for non-magic TBG. There's a big splitting associated with the non-interacting band structure. Then as you go towards the K point, you get the non-interacting Dirac cone that you get from the MacDonald model. But if you go towards the magic angle at charge neutrality, then you actually see that this gamma point area becomes gapless, whereas the K point, that you open up a gap at the K point. For this specific state, it's a bit unclear whether this is really the Mott semi-metal, because it's known that strain is an issue in the system, and in general pneumaticity can be an issue. So at the specific temperatures of this state, it's unclear whether this is the Mott state or some pneumatic state. But at least it's consistent with the fact that interactions are selecting out the gamma point. And other states are more consistent with there really being Mott physics and gamma point being special. Specifically, I want to showcase this plot here, which is takes a bit to internalize because there's a lot going on. So I apologize for that. On the x-axis is the twist angle, and so you can think of it as momentum. So there's gamma k m up here, and then the y-axis is filling. So here is nu equals 2 and nu equals -2. These are the these are the states that you dope in order to get the superconductor. And you can see that if you dope, depending on whether you dope electrons or holes, you get very different spectral weight. In either case, you'll notice that you see a spectral weight that's very spread out through the Brillouin zone. And this is zero bias tunneling. So if the normal state of the superconductor was some Fermi surface, you would expect to get a peak at KF. But there's no peak at KF. There's no sign of a Fermi surface at all here. And this is despite the fact that there's, when you dope away from charge neutrality, so nu equals 2 plus epsilon and nu equals -2 minus epsilon, there are light quantum oscillations. So we know from transport that there are light carriers here and that there are light carriers here. But instead of seeing, a Fermi surface associated with these light carriers, you get a kind of a wash in momentum space and suppressed spectral weight. And we think that this is at least consistent with there being light trions in the system, because this kind of solves both of these issues. They're orthogonal to the electron exactly, so you won't pick it up in electron tunneling, but they're also parametrically light, and so they could contribute to quantum oscillations. And now, I'm not saying that at all that this is like a smoking gun for these things. Ideally, you'd want to tunnel in and detect the trions themselves, but I think it's at least motivates looking harder and trying to see if we can detect these trions by doing some sort of assisted tunneling.
Question.
Yeah.
So, because this reminds me of like acoustic mode, like Goldstone mode, and
so how does it remind you of a Goldstone mode?
Because it's not allowed to mix at gamma bit. There is like, yeah, the way I'm thinking, like, is there a symmetry I could think of in this model that protects?
Yeah, so you can think of it not in terms of a broken symmetry. The state is symmetric under everything, but this trion has a different eigenvalue under rotation symmetry than the electron, so that makes it not mix with the electron. But in general, there actually has to be some point in the Brillouin zone where they don't mix, and that's a result of band topology. They have different Chern numbers, the trion and the electron.
Will it look like here as a spectral function?
Of electrons. If you do the trion spectral function, it'll be dark here and bright here. Yeah.
Very good question. In your model, do you really not have particle hole symmetry, or you have? And how to reconcile with this very much nu equals 2 minus 2 asymmetry?
Oh, because at -2, you heavily dope the system. So just doping breaks the particle hole symmetry. Even if you start with a particle hole symmetric model, this doping will do this. So the particle hole symmetry would be relating -2 to +2, but -2 itself will always strongly break it.
He's asking why is 2 and -2 different?
Oh, yeah, I mean, you can add particle hole breaking terms to the Hamiltonian, but whether those terms can cause you to fully reproduce the thing on the left, I'm not sure. Yeah. And there are various sources of particle hole breaking in the system. Yeah. Yeah. Sorry, is there another question? Oops. Oh.
You're saying that your green function at 0 frequency has no structure in K.
Right, has no
structure in K.
Structure. It has structure in K. Like the self energy that leads to this is strongly K dependent. But
you don't have any preference. From a surface normally means that green function at 0 frequency has strong structure in K.
Yeah, good point. Yeah, so in the experiment, it looks like there isn't anything. Yeah, and one can, I think, understand this by, like, if you're forced to tunnel in electrons, right, then you're forced to tunnel in something all the way over here, right? And the electrons, like, there's not much weight here, so you can imagine that you won't really get much structure in space. And so if you're forced to tunnel in an electron, that electron will then be forced to be away from gamma because there's no weight at gamma. You can see here that there's no weight at gamma when you try to tunnel. So it's not that it's flat in momentum space everywhere. It's actually, there's nothing at gamma consistent with there being nothing here. But away from gamma, it's kind of flat, consistent with this being kind of flat. And so you imagine that you're forced to tunnel over here, and then this thing decays into a bunch of trions. So you get something pretty incoherent. Yeah. Okay. So I'm going to close with the TVG story. So if there are any questions about just about graphene, this would be a good time to ask them. But overall, I want to summarize that stepping back a bit, we kind of put two ingredients in: concentrated charge or Berry curvature, together with a isolated topological band. And this leads to a parametrically wide Mott regime with a small parameter S squared, where these orthogonal and light trions appear out of the calculations. Yeah, I think some open questions include, can we actually detect these things experimentally through assisted tunneling? And then that would kind of enable us to start asking questions similar to those in the cuprate, because we could actually see the low energy carriers that are about to pair. And then likewise superconductivity from trion pairing. And also, since these ingredients, I think, aren't so model specific, you could imagine many systems that could have concentrated charge density and band topology. Are there other systems that do this? Yeah. So yeah, we about to ask something?
What's going to happen at lower temperature? Do you have any idea?
Yeah, it's a really good question. So if you just do the very leading order expansion to this, I'll say a bit more about this, but Erez will probably say even more. If you just do the very leading order expansion to this, there's an order of limits issue between small s going to 0 and temperature going to 0. And that's really, there's a physical reason for that, which is that there are exchange interactions that are on the order of s squared. So this is, all the calculations here are assuming temperature is much bigger than this exchange scale. Then separately at low temperature, it's a harder problem. You can do like Hartree-Fock, and that gives you these intervallic spiral states. And those have also been seen experimentally. So there's some transition from this high temperature state to this low temperature state. And that's probably important to understand if you want to understand all the weird physics that's about the superconductor. And I think that is a little more tractable than we thought a year ago. Yeah.
So, but you expect a phase transition or not?
I think it's should be a crossover. I don't until you get, at least until you get to one of these phases, and even then, I guess these can have BKT transitions.
You expect ordered state at lowest temperature, right?
I don't think that's probably the null hypothesis. Yeah.
The things without strain, we know it's 0. Some of these states can be BKT.
Can be ordered, yeah. So there's a situation where if you don't have any strain and you look at charge neutrality, then we know the ground state exactly, and it's an ordered generalized ferromagnet. How much time do I have left?
We're going to show you this.
5 minutes.
Before questions.
5 minutes before questions. Okay, cool. That's good. So now I want to step back a bit beyond twisted Bilayer graphene and kind of take this tool seriously. The fact that we were able to take a system with very strong local correlations, but also very important non-local aspects coming from band topology, and kind of merge them together. And so we're kind of interested from a formal theoretical perspective on what this expansion can do. And in particular, can we do it? You can apply. It turns out you can write down models beyond twisted Bilayer graphene, even including trivial Hubbard bands, where this s-squared parameter can enable a lot of analytic progress. So I want to give a flavor of this now. So this is a recent paper that came out, I think, yesterday with Pasha Nosov, who's here, and Islam, who is also here. I also want to point out that there are 3 other papers that appeared a couple weeks ago that are kind of also developing this expansion to higher orders, but applying it to the specific case of the Song-Bernoulli model in twisted Bilayer graphene. And when comparable, we obtain results that are compatible with them. But one thing that I think we're pretty excited about, and I'm going to emphasize here to kind of orthogonalize with respect to those talks, is that we can do DC transport analytically, which I think is a pretty unique thing. I don't know of really any other way to calculate transport analytically in 2-dimensional strongly correlated systems. So the setup kind of goes like this in the most general sense. You have a Hamiltonian that has a local part and a non-local part. This non-local part can just be an ordinary hopping. It can be a correlated hopping, and these correlated hoppings are naturally generated in models with band topology, where the quantum geometry gives you non-locality. And also it lets these like correlated hoppings induced by interactions projected to topological bands. They generate things that look like electron trion hopping. That's why the dispersion I showed you almost looks like non-interacting dispersion with a trion. And so one nice feature of this is that we'll be able to treat electrons and trions and other multi-particle operators all on the same footing.
So this is a quadratic Hamiltonian?
It's secretly not quadratic because these can be multi-particle operators. So the gammas don't have canonical commutation relations.
Well, twin gammas could be C's, but then H local is always non-quadratic.
Oh yeah, H local is always non-quadratic.
H local is non-quadratic.
So it's like
Yeah.
property or
Okay.
I'll have a more concrete, I'll have a real simple one on the next slide. But generally you can have any local part and any non-local part. The important part of this non-local part is that it has a small overall coefficient. So you have a very small amplitude to hop. But when you do hop, you generically go for a pretty long distance. And that's associated with having this small momentum space scale on the order of S and an order 1 bandwidth. And it turns out that you can do an expansion around H local in general for any hopping. And this was done in the so-called linked cluster expansion 1990s by Metzner. But this is actually a pretty tricky and kind of sick expansion if you just do it perturbatively. But if you augment it with small s, then you have to do some resummations associated with hopping from site to site to site to site, because there's a coordination volume and overall coefficient canceling out. And when the dust settles, it turns out that you really want to count loops as opposed to hopping lines. And so you have to resum all of these things. And that gives you a scheme to actually calculate order by order in S squared in a kind of non-pathological way. And it really just amounts to a loop expansion in these hopping loops.
So all these diagrams are S squared, right? So you need to
all of
add
these
the
are.
full.
Yeah, so you resum this and then you put that there. Yeah. And there's a pretty did I mess this up? Oh yeah, I want to do this one. There's a pretty the simplest case is just if you have a Hubbard model, so a Hubbard U interaction that you expand around, and a dispersion that looks like this, where it's flat almost everywhere in the Brillouin zone, but then it has an order 1 bandwidth, but this order 1 bandwidth takes place in a order S area of momentum space. And you can take this and you can expand in S, and there are some nice features of this, which is that you can get quasi-particles associated with this highly dispersive region. These quasi-particles are highly mobile. They can move very fast and very far, unlike quasi-particles in typical Mott systems. And they actually have a parametrically small amplitude to scatter. And we can compute their scattering. They have a lifetime on the order of 1 over T naught S squared, so parametrically long lifetime and a parametrically fast velocity, despite the fact that this is doping a Mott insulator. So this is a picture of the lower Mott band. You can see that, and this is with an analytically calculated lifetime now. The previous ones were brought in by hand, but this is really an analytically calculated lifetime now. And for a very, very small value of S for illustration. And you can see extremely, extremely sharp quasi-particle peaks. And then from this, we can actually do transport. I'm not going to go through the results in detail. I'm just going to point out that we can get a wide variety of transport regimes. I'm going to highlight 2. The simplest one is the really high temperature regime, which is a bad metal. Here, the holes are long-lived, but their occupation in momentum space is totally thermally incoherent. And it turns out that this gives you this bad metal T-linear resistivity. But then at low temperature, on the order of some small number times the bandwidth, so it's not parametrically small, but for some reason there's a small numerical factor here. The holes become coherent in momentum space, and they occupy a pocket around this gamma point region, and they have and so these holes form a Fermi surface. They form a small Fermi surface, so volume delta, and so we called it a thermal FL star because this volume is the same as a true quantum FL star regime, but it's a thermal FL star because you don't have a spin liquid, you have fluctuating moments that are thermal. But you have a separation of scales between the the Fermi surface is parametrically coherent. And in this thermal FL star, you get some constant resistivity times S squared. So we can really access a very wide variety of transport regimes, and all of these calculations are totally pen and paper. Yeah.
Can I slow you down for a second?
Yeah.
So this is the
basically done.
This is the resistivity at some partial filling of the band. No disorder. Am I right?
Correct.
No disorder.
Yeah, you can dope however much you want.
And so So at zero temperature, there's no resistivity. And finite temperature, the resistivity is because of electron-electron interaction.
So this isn't actually zero, and that's because we don't really go to low zero temperature. We go down to temperatures of order S squared.
But you'd expect the resistivity to be zero at zero temperature, no?
Yeah, but we don't access zero temperature in these
Fine,
calculations.
but we have this point, I think, is something we know.
Probably, but yeah.
And then the high temperature resistivity that you calculate, that's by electron-electron interaction.
It's electron-electron interaction is kind of the starting point, and then it's from the hopping. Yeah, that sounds good. Yeah.
Okay, first, thanks very much.
Thank you. Oh yeah. Yeah, we can do the topological case too. Yeah.
Okay, thanks. Questions?
Can you go back to the resistivity? So what are the different curves? I can't see the.
Oh yeah, sorry. I couldn't find a plot that did both of these, and I didn't want to force Pasha to do something early this morning. So I apologize for the. It's hard to see all the regimes in a single plot. But I focused on this one because it shows this one simply. And over here, this is a non-zero constant. So I can draw it as better as a cartoon.
What are the different?
These are different densities.
Oh yeah, they're different densities.
So
Yeah. So it's
this is one, and this is one. No. In the end, left side.
Yeah. So this is if I do rho over S squared, this is order one.
Yes, that's what I'm asking.
Yeah.
A similar question to the one by Adi. DC conductivity requires the momentum sink. Electron-electron interaction conserves momentum.
Yeah.
This specifies the momentum relaxation mechanism.
Yeah, this is in the regime of fluctuating moments. So you have fluctuating moments at every lattice site. And so umklapp is very plentiful.
Which means you would get zero in the continuum translational invariant model, right?
There isn't a continuous translational invariant model that well describes this regime. The lattice is well alive. There are fluctuating moments at every lattice site. There's an extensive entropy. And you can think of it like at every lattice site, each fluctuating moment kind of behaves like an impurity. And electrons are just scattering off of these fluctuating moments as if they're impurities.
So can you guess the proportionality factor? I mean, not to the level of pi over 3, but in terms of units, it's going to be h over a squared times t over what?
So we can compute the proportionality factor, and Pasha, please feel free to jump in. I don't know where you are. Yeah.
It depends on the density.
Yeah, it depends
I don't
on
remember the exact.
Yeah, but I'm trying to understand the units. What will give something that has the units of resistivity?
Yeah, so it's S squared you can think of as being dimensionless.
Yeah, and so we need the temperature divided by some energy scale that's a function of density. If I understand correctly, the Fermi energy has no meaning here.
Yeah, so you can take just a Drude-like form. So n over m and then you just need a tau. And then the tau is T naught S squared.
Are you asking about the linear part or the constant?
He's
asking about the linear part.
Like thermal fluctuation, right?
Yeah, well, at the very highest temperature, yeah.
But is it the same regime at very high temperatures and down to the temperature for your bed metal beginning?
No, there's a crossover at the scale, at a scale like on T star, which can depend on density in a complicated way. But at its peak, it's basically order one.
What is the right direction is at low temperatures compared to star?
Yeah, so this, so T star is maybe down here, but T star isn't small in S.
Right, actually, then you are at temperature electron side of the
Yeah, this stuff is high temperature, larger than T star. Yeah. It's thermal regime for the charge.
Yes.
I'm always in thermal regime for the spin, but the T linear is thermal regime for the charge. So I think this T linear is basically the same T linear as people see in like DT or high temperature expansion. It's It's incoherent charge randomly occupying stuff.
So the linear T just persists.
Yeah, it's like compressibility linear in T, high temperature expansion style.
Okay, sorry. More question. Not, thank you very much.
Thank you. Yeah.
Silence.
I should have my own. Try to use that. Oh, wrong titles. But yeah, that part is correct. Yeah. Okay, so yeah, we also do this. I hope it's the right talk. Yeah. So yeah, so it's always a pleasure to be back here. I'd like to thank the organizers for the opportunity. Some of you have heard a version of this talk, but and some have not. So I'm going to go through it normal pace. But so yeah, if you're jet lagged, Europe or West Coast like me, feel free to doze off. I'll wake you up. There's going to be a new part, some new results at the end. So this talk is going to be very closely related to what Patrick was talking about on twisted bilayer graphene, focusing on twisted bilayer graphene. But as Patrick described, there's both new experimental developments and new theoretical developments that we're very excited about. And I think some of the puzzles in this system are being clarified. Right, so this part is really going to parallel what Patrick was saying, right? So Moiré materials really offer a new route to realizing flat bands, right? So one route that we knew for a long time is if you just put electrons in a very deep potential, and you have electron-electron interactions, the electrons are going to tend to localize. In the extreme case, just one electron in every lattice site, and that electron is going to have a free spin moment that can fluctuate. The other extreme is a quantum Hall system, so also realizing flat bands, but very, very different flat bands. So here you just apply a larger magnetic field, and you get Landau levels which are flat. But these are, of course, topological flat bands that cannot be described in terms of completely localized orbitals, orthogonal and symmetric orbitals, and they give rise to very different physics. The electronic wave functions are delocalized, so they overlap. They can give rise to a quantized Hall effect. This tends to also give rise to generalized ferromagnetism because of direct exchange between these wave functions and so on. And for a while, there has been this open question, okay, how should we think about these new types of flat bands that you get in twisted bilayer graphene? Should we associate them with either one of these two extremes? And the confusion was, at least for me, is that they actually, experimentally, they actually show properties that you would associate with either one of these two extremes. Okay, so first of all, it was identified early on theoretically that these narrow bands at the center of the band structure are actually topological. So these are flat topological bands. They support a subtle form of a topology called fragile topology. So at least I expected them to realize some version of generalized quantum Hall physics, and this indeed happens. So we know that the ground states as a function of density are over much of the phase diagram realize some kind of generalized ferromagnets. Okay, so it's not usual ferromagnets because you have spin and valley and orbital degrees of freedom, so you have to determine how these degeneracies are being lifted. But for instance, close to nu equals 1, there's some kind of spin and orbital ferromagnetism, which was observed in some samples at least. And in a range of dopings between 2 and 3, there's a different kind of symmetry broken state, which is the so-called IKS, or intervally spiral state, which is also observed. Okay, so this is sort of what you would expect in a multi-flavor version of a quantum Hall system, essentially. On the other hand, we know that these systems can actually display behavior that we would associate with localized moments. Okay, so if you have localized moments over a broad range of temperature, you should expect a large entropy, which is quenched by a Zeeman field, and this is exactly what's observed. Okay, the first hint of that came from transport. Okay, so some resistive features shift in an interesting way as a function of temperature, suggesting that actually the more correlated state has a higher entropy. And this was later confirmed both by Shahar-Ilani's group and by Andrea Young's group by using thermodynamic relations, inferring the entropy from compressibility, from temperature-dependent compressibility measurements. And indeed, there's a large density range where there's a huge entropy of the order of 1 kb per Moiré unit cell, and a big chunk of that entropy is quenchable by an in-plane magnetic field. Okay, so this is really behavior, and in fact, the field that you need in order to quench that entropy depends on temperature, exactly in the way that you would expect from a localized electron that has a fluctuating spin moment. Okay, so somehow these electrons manage to be topological and localized at the same time, and this is exactly the puzzle that Patrick was discussing. Okay, and a very convenient way to think about the structure of these flat bands is the so-called topological heavy fermion basis or description. Okay, and the idea is this: it was observed early on, actually, both theoretically and experimentally, that the structure of the wave functions in real space of the electrons in these flat bands is actually not uniform in the Moiré unit cell. Okay, so I'm showing here a calculation from Kaxira's group, but this was actually observed directly in STM, as Patrick showed. So the wave functions that consist of these flat bands are not uniform. They're actually very concentrated in a particular region of the Moiré-Brillouin zone, the so-called AA region. Okay, and there's a theoretical framework of Sung and Bernavig that basically encodes this fact. So it turns out that the bands are topological, so you cannot span the entire band using a well-localized 1E orbitals, but you can find a basis, which is not the actual band basis. It's not the basis of the Bloch bands of the actual single particle bands, where almost the entire flat band can be spanned by localized Gaussian-like orbitals that are concentrated in the vicinity of the AA sites. And you have a missing a part of the Brillouin zone where you cannot span the flat bands using these orbitals because they have the wrong quantum numbers. And to make up for that, you have to include a pair of remote bands from either side. Okay, so there's a different orbital that actually actually captures the Bloch state over here. So there are two types of orbitals in this description, and so basically 4 of them are called C and 2 of them are called F, and the hybridization of these orbitals basically form the actual single particle bands. And importantly, the f orbitals by themselves are basically completely localized 1A like wave functions. Okay, so this resembles a heavy fermion model, hence the name. Okay, so there are two types of electrons, very localized and very flat dispersing electrons and very strongly dispersing electrons. But here the dispersing electrons are actually Dirac-like. Okay, so if you artificially turn off the hybridization between the two types of electrons, you would get a dispersion like this, a band which is a pair of bands which is completely flat, and Dirac-like strongly dispersing electrons. These are the F and C electrons, and they hybridize, but the hybridization is most effective in the vicinity of the gamma point. Okay, so we're going to use this basis in order to solve the interacting problem and get results that basically agree with what Patrick showed. Okay, so what does the spectral function of this kind of system look like when you add a strong interaction? And in particular, one thing that we expect interactions to do, so these very localized 1A orbitals, the AA sites, would have a local Coulomb interaction. So you expect, at any integer filling, at least you would expect to see a Mott-like gap, at least in some part of the Brillouin zone. Okay, and so there were some calculations of what the spectral function looks like at intermediate temperature. Okay, above any symmetry broken state that might occur at zero temperature. So this is a quantum Monte Carlo calculation at charge neutrality, where if you assume particle symmetry, there's no sign problem, and you see this dispersion. So there are two features, two bands that look very flat and occupy most of the Brillouin zone. Okay, at a energy of plus or minus 20 or so millivolts. And they're sort of gapped everywhere, with the exception of the vicinity of the gamma point where that gap collapses. Okay, so this is the sort of hybrid behavior that Patrick showed in his talk. Okay, over much of the Brillouin zone, it just looks like a Mott insulator. These are Hubbard-like bands, with the exception of the gamma point where it looks like a semi-metal. Okay, and this type of behavior was actually seen in various different types of calculations. In DMFT, people see similar things, and also Patrick showed an analytic way to compute this type of spectrum. So this analytical work that Patrick discussed takes advantage of the hidden small parameter of the problem, the so-called S, which is in the topological heavy fermion language. That's the area, that's the fraction of the Brillouin zone occupied by the C electrons, or where the hybridization between C and F is very strong. So that's the part of the Brillouin zone where there is a strong quantum geometry, where the Bloch wave function actually varies rapidly, whereas far away from this region, the Bloch wave function is more or less K independent. Okay, so this is what we'll focus on, but this is what I'll focus on for the remaining of this talk. So it's really a new small parameter that we, at least I didn't know until this work pointed to that can actually be used to obtain non-perturbative in the interaction results and solve the many-body problem. I think that's really exciting. Now, the thing that really confused me when I first saw this, and I discussed that with Patrick. So the width that you see in these spectra is actually artificial. If you do the calculation to the lowest order in this parameter S, as they did here, what you get is really that the spectral function consists of dispersing delta functions. So the width is actually 0. Even though this is a very strongly interacting system, you get infinitely sharp quasi-particles, basically. Okay, so why is that? So that motivated us to examine this problem from using the language of the topological heavy fermion framework. But I want to emphasize that this is just a choice of basis. Okay, so it's the same problem that we're solving. Okay, the nice thing about using the heavy fermion basis is that we don't have to project to the narrow bands. We also have access to the remote bands. seen here. Okay, but we can take the limit where the interaction is much smaller than the hybridization, and we would just recover the same results. Okay, so I'm going to show a little bit of some formalism and some calculations. Okay, so this is the action of the topological heavy fermion model. So there are two types of electrons in the model. There's C electrons, 4 of them actually, four different C orbitals, and a pair of F orbitals. For the most part, the only interaction we'll take into account is a local Hubbard-like interaction on the F sites. It turns out that interaction is the most important. There are other interactions that can be included perturbatively and don't change anything qualitative, we believe. Okay, and very importantly, there is a hybridization term between the C and the F electrons that has a particular K structure. Okay, so that's the model that we want to solve. Okay, and now we're theorists. We need a small parameter. What's a small parameter? Obviously, we don't want to perturb in the interaction because the effects of interactions are very non-perturbative. We want to describe something which is almost Hubbard bands. Okay, and the trick, as we saw, is to use this so-called S-squared parameter. Okay, so once again, this is the dispersion with the hybridization between C and F turned to 0. Okay, so we get here the flat F bands and the very strongly dispersing C bands. And as long as basically the strength of the hybridization at the gamma point is small compared to V star, the bare velocity of the C electron, times the size of the Moiré-Brillouin zone. Okay, so this is our small parameter. Okay, so the F and C electrons are only going to hybridize in a region in a fraction of the Brillouin zone of order S, where S squared is this parameter. Okay, so that's our small parameter, and importantly, V star, the speed of the C electrons in the topological heavy fermion model comes out to be of the same order of the bare graphene velocity. So it's a very high velocity. This is very, very steep. Okay, so this is why this is actually a small parameter. So as Patrick showed, this is about a fifth or
what is GM?
Yeah, so GM is the size of the Brillouin zone, mini Brillouin zone. Yeah.
It doesn't depend on you.
Yeah, so the actual parameter that you see at lowest order in the calculation is this, but yeah. So this is a hybridization function. It's really it's a local density of states of the C electrons, but we take it at the frequency of order U, and this is linear in U because it's Dirac. So the U actually cancels from this. Yeah.
For connection with previous talk.
Yeah.
In Patrick's talk, dispersion was taken to be picked at some particular K point.
Yes.
Here you have hybridization essentially picked.
Yeah.
Is it just change of basis? Or?
No. So if we take this to be exactly at the magic angle, there would be what would happen is that a gap would open between the flat bands and the remote bands, and there would be no dispersion whatsoever at the single particle level. Okay, and then we can deviate from the magic angle, and we'll get a dispersion which is peaked at gamma, exactly like Patrick showed. Yeah, Andre.
So, Erez, just to dispel a lot of the confusion. So, would you say, looking at the formula as we pointed out early on, that basically it is independent of U because, of course, as you just said, it's linear in K.
Yes.
But then this is the same as hybridization expansion.
Yeah. So right. So it's a.
So basically, the small gamma and the large gamma limits.
Yeah. Yeah.
The small U and the large U limit.
Right.
Not depend on this. This parameter can also be just the usual hybridization expansion.
So yeah, so I mean,
that's
true. You would have to resum the hybridization expansion in a particular way, right? I mean, so it's not lowest order in the results I'm going to show are not going to be lowest order, right? And this is what you're doing also.
So first order here matches the first order.
Of course, yes.
Okay, very good.
Okay, great. Other questions? Yeah. Okay. Right. So yeah. So how do we in this formalism, how do we make use of this small parameter? Okay. So we want to be able to expand any quantity to any given order in S squared. And we found a way to do that. So it's done by the following steps. First of all, we take this action and we basically formally trace out, we formally do a hybridization expansion, like Andre said. Okay, so we basically formally trace out the F electrons order by order in the hybridization, and we get an effective C-only action. Okay, so SC is just the a non-interacting C-axis, C action, and we get infinitely many vertices between the C electrons that are coming from tracing out the F electron. Okay, so we trace out the F electrons with respect to the zero hybridization action. So these vertices gamma. Okay, so they're basically n C electrons coming in and n C electrons coming out. The vertices are composed of local n-body correlation functions of the F electrons with respect to the local single site action of the F electron. Okay, which is just a Hubbard U. So this is in principle solvable. It's a very complicated correlation function because it's an interacting problem, and also a time dependent or frequency dependent. But that's the effective action that we get. Okay, so looks very complicated, and it is very complicated. Okay, so this is what it looks like. Now, the first term in this expansion would be simple. So if you just look at the two-body vertex for C electrons, that's just proportional to the one-body correlation function of F electrons that we can compute. Okay, and that's a quadratic term in C, so we can actually incorporate absorb that into our C electron action. That's a quadratic action, and we can try to expand in all the other vertices. Okay, so there's here's the gamma 1, the one-body C vertex, and gamma 2 and gamma 3 and so on. Okay, so how do we treat this this action? So here we have to appeal to the small s expansion. Okay, and it actually comes to our rescue. So if we compute any quantity, for instance, suppose we wanted to compute the C electron self-energy, okay, we can expand it in terms of these vertices. Okay, so here once again the lowest order is the gamma 1, and then there's a gamma 2 with 1 C loop and gamma 3 with 2 C loops, and we can compose different vertices in different ways. But importantly, it turns out that any C loop in this problem would actually contribute a factor of S squared to our expression. Okay, so where does that come from? So that simply comes from the phase space, the low energy phase space of the C electrons. The C electrons are only living in a fraction of the Brillouin zone, which scales like S squared. So each time we integrate over the momentum of the C electrons, we're going to extract a factor of S squared. Okay, so this is what saves us. It really is a loop expansion, as Patrick described. Okay, now the gamma 1 we actually have to treat non-perturbatively because I can decorate the C line by any number of gamma 1s without adding any loops, but then all these higher order loops would be suppressed. Okay, so right, so now there's actually a divergence of the self-energy at a frequency of order of the Mach band. We have to resum that, but let me not go into that detail, into details there.
What is N sub F?
What is N sub F is the number of fermion flavors. Okay, so that's 8.
You do a 1 over N expansion?
So this summation, in this paper, we do it using the large NF expansion. Since then, I think now we know how to do it without appealing to the large NF limit. We know how to resum this exactly. But yeah, I don't want to discuss that in detail. Okay, so here are some results. At zero loop order, we get these sharp spectral functions describing Mott-like bands over most of the Brillouin zone and semi-metallic behavior close to the gamma point, exactly what Patrick showed. This is actually exactly the same as the so-called Hubbard 1 approximation applied to this model. That just coincides with the zero loop expression, but then we can do the loop expansion, and we get that the bands actually broaden. And interestingly, this width can be actually quite substantial. Okay, so it's of the order of few. When gamma is very large, that's basically the only energy scale in the problem. It has an S squared. So it's the lowest order correction, but it's actually proportional to this number NF, which is not small. It's actually 8. This is why these bands look kind of broad. Okay, so by the way, interestingly, the C electrons are still very sharp within this calculation. Yeah.
So your calculation is zero temperature?
Yeah, so same as Patrick, this calculation is in this regime of temperature much smaller than U, but much larger than S squared times U. This cannot be a zero temperature answer by no means, because this state has tons of entropy. The state is a very high entropy state. It has these fluctuating spin and valley moments. Okay, so something would have to happen below a temperature of order T times S squared. Yeah.
How come the temperature constant from 1 over tau?
Yeah, so the reason is basically what Patrick described. So at least it's easiest to understand from if you think about the lifetime of the C electrons, which is not zero, which is not infinite. Okay, so the C electrons are basically feeling the F electrons like localized moments. Mm-hmm. It's like T-independent scatters in this regime. Okay, now higher loop corrections will give you temperature dependence. Mm-hmm. Okay,
but for the summation at omega close to U over 2.
Yes.
Then you probably don't need any temperature.
That's true. Yeah. Okay, so now in principle, using this expansion, we can calculate any quantity we like, not just the single particle Green's function. For instance, we could look at the flavor susceptibility, and that can also be done. It turns out that actually follows this Curie-Weiss law with a Weiss temperature, which goes like U times S squared. Okay, so this actually shows us, this is the signature of the first thing that will break down at low temperature. So basically the flavor susceptibility will diverge at Q equals 0, and we expect some kind of symmetry breaking. Interestingly, we can estimate where this behavior would actually break down, and it would break down down to a temperature that goes like the Weiss temperature plus a correction, which is S to the power 4. Okay, so that means that this is a mean field like a divergence of the flavor susceptibility, which persists down to a very narrow regime around the Weiss temperature. So this means that whatever transition occurs here is expected to be very mean field like. And I think we understand why. The reason is basically if you think about these flavor moments, they interact via very long range exchange interactions that go through the C electrons. So that's the reason for that. So we think we actually have pretty good control over this entire regime down to a very narrow temperature range close to the symmetry breaking transition. Okay, so how much time do I have?
About 5 minutes.
5 minutes
before.
Yeah, yeah, good, right. So yeah, so using this approach, we can actually we can also calculate the spectral functions away from charge neutrality, and this is what they look like at integer fillings. Interestingly, there's this in addition to the particle asymmetry in the spectrum itself, there's also a very pronounced particle asymmetry in the width when you go away from charge neutrality. And Patrick showed the QTM experiment from Shachal-Ilani's group, okay, that close to the magic angle shows this precisely this kind of a Mott semi-metal behavior that was expected, and this made everybody happy because it looks very similar to this. But of course, a strained semi-metal would actually have a very, very similar spectrum with these gapped and flat bands away from the gamma point, and the gap closing at or near the gamma point. So the question is, in this experiment, what's actually seen? Is this a strained semi-metal, or is this the Mott? Is that this Mott semi-metal? And we don't know yet in this particular example. Okay, so there are many experiments in TBG, and of course, every sample has its own strain. There are many experiments where we know that what we see is actually the strained semi-metal from various evidences. Andre might talk about the difference between these two states and their Landau level spectrum. Okay, but I want to just show one more result about what the spectrum of the the strain semi-metal in more detail is actually supposed to look like. And here we discovered something we didn't expect. Okay, so this is a quantum Monte Carlo calculation, and the spectral function here is computed using a numerical continuation to real frequency, but we can actually calculate the spectrum of the anisotropic semi-metal using the same small s expansion. Okay, so we did that. We know how to introduce strain into the topological heavy fermion basis. Okay, that's done in this paper. The main thing that strain does is actually extremely simple. It simply splits the energy of the two f orbitals. Okay, so these two f orbitals under C3 symmetry behave like px and py. So strain picks a direction. So it actually splits the energy of these two orbitals, and it does so extremely effectively. So a heterostrain of just a fraction of a percent can give you a few millivolts of splitting between these two orbitals. And my student Al Keshet did the calculation, and this is what it looks like at a certain strain of say 0.2%, and for a certain value of s squared. This is actually just a little bit below what we think is the physical value. And you see this interesting structure. The bands are very sharp, close to the gamma point, but then in a sudden way they become broadened. There's even some kind of avoided crossing-like feature here. Okay, the sudden broadening you can understand very simply. If you have the splitting between the two types of f electrons, there's a finite energy excitation of the system, a neutral particle hole excitation of taking one favored f and exciting that to an unfavored f. Okay, and that excitation has an energy of 2mf, okay, which is exactly here. So basically, once the C electron dispersion crosses 2mf, the C electrons can undergo inelastic scattering from these particle hole excitations, and they broaden. Okay, but then as we increase s squared, something more interesting happens.
So this is temperature above the strain scale or below the strain scale?
This is temperature 0. Okay, so here we can actually safely take the temperature to 0. Yes. Okay. So this is what happens as we fix the strain and increase s squared. So you see that this type of avoided crossing sort of persists over a broader region, and ultimately we actually get a new band. Okay, so there's a new band excitation which is seen in the single particle spectral function, which is living right or just below an energy of 2mf. Okay, this is really induced by the strain. It's really tied to the strength of the strain, and the original mid band becomes so broad. It's still there, but you just can't see it. It's broadened so much, whereas this new excitation is very sharp. Okay, so we think we understand now what this new excitation is. It's a trion, not quite the same trion as Patrick was discussing, because it doesn't live close to the gamma point. It's basically a bound state of the particle hole pair excited between the favored and unfavored f bands, bound to a C or f electron or hole. Okay, and this is very analogous to what happens in a very old problem, the problem of electrons coupled to an Einstein phonon. Okay, so suppose we have a phonon, an optical phonon, which has a frequency omega naught, and it's very well known that when the electron dispersion crosses this frequency of omega naught, the electrons start scattering, the effective mass changes drastically. But in fact, if you work it out, there is this excitation which actually persists at the frequency of omega naught. Its spectral weight becomes exponentially small when you go away from the crossing point. That's why, I guess this is why it's not discussed very much. But in TBG, this band is not dispersing, it's actually flat. So this is why this actually can have a substantial spectral weight. Okay, so yeah, let me finish there. And yeah, thank you very much.
Questions? Yes.
So in the experiment paper, which I think you're a co-author,
yes,
the author go at great lengths to try to rule out strain as an explanation for this feature by saying that it's really stable throughout different regions in the sample across strain.
Yeah.
It seems now you're suggesting that the explanation for that feature is still strain. So do you understand why it seems to be it doesn't change across various values of strain?
Yeah, no, I don't understand what one of the things we're trying to do now, and I think might be interesting to do, is, the effective strain would be amplified by the interactions, and we're trying to see if we can get a substantial enhancement. So there's a strain susceptibility which also becomes very large. That requires, tweaking this calculation a little bit. No, I don't really understand why that feature is so robust in the experiment.
So you consider uniform strain and
yes
in the calculation, and
yeah,
I've just pointed out this issue. But if I now go back and I think also that besides the uniform strain, I also have strain fluctuations.
Yes.
That are very anisotropic.
Yes. Yes.
So my question is, you show these pictures of the band along a particular cut, right? You're going
yes.
to go
Yeah.
K.
Yeah.
Does it look this?
No, it doesn't look the same.
So there is an anisotropy.
Yeah. So in fact, you see that here, these bands don't touch.
I can't see it, but that's okay. I believe you.
Oh,
no, it's just me. It's not their figure. I'm in denial of my age. It's okay.
Okay. Yeah. So these are actually Dirac points that are off the axis that is scanned.
I see.
I don't have it here, but that's a very good point. So so let me comment about that. This is a cut through the spectral function along a particular cut.
Right.
Now the QTM actually cuts along three symmetry related cuts. So we computed the QTM spectrum from the same model, and you actually see the three cuts are different. Okay, so if you don't broaden too much, you actually see three dispersions superimposed on top of each other.
So this is a half filling, right?
This is a half filling.
And so if I did Hartree-Fock,
yes,
I should get this.
Yeah, so you wouldn't get this. This Trion you would not get from Hartree-Fock.
Well, by Hartree-Fock I mean just I could do more commutations if I want.
Yeah, so you would get the ground state is just a Slater determinant, so that you would get exactly. But I think that to get this excitation spectrum,
like for example in the time dependent Hartree-Fock, right? I get more.
Yeah, so you would need to go beyond time dependent Hartree-Fock, right?
Because I would get this.
Yeah, so this Trion.
Yeah.
Well, I mean, yeah. So this broadening definitely you won't get.
Sure. I agree.
Yeah.
Okay. Fine.
Is the spectral weight of this strain-induced Trion small n s, or no?
Sorry, is the
spectral weight of the strain-induced Trion small n s squared, or
no?
It's not.
I don't think so. Let me think about it.
So you are dealing with the most semi-metal limit where gamma is smaller than U, right?
No. This is actually gamma larger than U.
Okay, I see.
Yeah.
So it's
this is why you actually don't see here the remote bands.
Small n squared.
Without the strain, is it the same limit?
Yes.
Okay.
Yeah.
So it's like the opposite limit compared to Patrick.
It's the same limit as what Patrick was discussing. So basically the limit where essentially you could have projected everything and you would get more or less the same things. Okay, so a band gap is larger than U.
All right.
Yeah. Yeah.
If you close your eyes for a second and make S larger and larger,
yes,
will you see that the two bands start coming closer to each other?
Yes.
I mean, that's a
yes.
So you can see metal insulated transition.
Well, yeah. I mean, at some point, of course, the expansion stops being
Right.
valid.
If you
Yeah.
Let's just see how it goes.
Right.
Whether it's something close in the middle,
Yes.
the region of final density of dangerous being lost.
Right.
What's your argument? More questions? Not. Thanks very much. Plenty of places around, some solid places, sandwich places. So much of your own.
It's like getting condo.
That will gain here. This is.
It's a different kind of target.
Именно, но просто
We had a good meeting with Eric last year.
Oh, good.
Yes.
So I still follow this.
I know, but
Надо копаться. Ну вот какой-то физический аргумент, что вот там dipole ну что оно сразу выступит, там пчелы.
So there's not a
Это вопрос, надо предложить потому что ну то, что ты там, если тебя там тестируют,
Piece этого числа, for this Trion that I have said that I had here, and like this anomaly in the QT, you wouldn't expect that you're in the regime. Within the light regime, yeah, it's the Trion gets replaced with an electron.
окей.
That band is super far away. So then, as you go, you expect to get a from the surface.
It's okay. Just you start writing one more terms.
But they're adiabatically connected in the sense that you can adiabatically deform the Trion into a sealer.
I think I got the worst.
One limit you get a Trion, one limit you get a sealer. So in the middle, that's hybridization of sealer.
Okay.
Yeah, I didn't make that. Do I see that? What's the
It's not like 60 in these.
I mean,
50, 60. The U over 2, which is like, gamma is like half the gap. U over 2 is like half the gap. U over 2 is like 15. Yeah. Directions go like gamma over U. US2 is the ionization. It's like